component of the course where we're going to be talking about test cases and where they come from, and particularly this issue of coverage testing. Okay. So you'll probably find videos of this elsewhere where I give a more complete coverage of this. But there's a whole bunch of algorithms, a whole bunch of approaches that guide us to systematic testing of code. Systematic testing of systems. And they include algorithms which operate on states, based on transitions, techniques known as identifying prime paths that do coverage testing. And I think some of you, I think one or both teams, I'm trying to remember it, at least one team, maybe both teams, are doing coverage testing right now. You have a certain stated coverage of your code, right? Yeah? That's great. Makes me, you've done me good. Well, okay, so first of all, both teams are doing it. Maybe they are. I'll have to go back and look at ID4. But if they're not, they could be. Turns out that is what you're measuring there is aspect of statement level coverage. And you can do coverage testing in broad varieties of ways. So what is this slide illustrating? Anyone recognize this? Oh, wow. What was that process that was illustrated here? Yeah, it's using an ATM machine. So it dispenses payments, right? Dispenses bills to you. This is a black box description. We're not depicting low-level code here. We're not depicting a certain algorithm in terms of the statements. We're depicting states of the machine or actions to be undertaken. So, person inserts ATM, and if it's recognized, it'll prompt them for a PIN, otherwise it ejects the card. If you've entered the wrong card, if you've stuck in a card for the library or whatever, it'll reject it. Otherwise, it prompts you for a PIN. You can enter the PIN, and if the card's expired, it will confiscate the card. Just sit in. Keeps it there. Has anyone had that happen before? Yeah, it's kind of interesting. Where'd it go? It eats your card. So if it's expired, if it's not expired, if this is a lost card, it will also confiscate it. If someone's reported this as lost. That's it. Yeah, sorry. Otherwise, it checks the PIN, and if it's an invalid PIN more than 3 times, it will also confiscate a prompt return. This kind of maps out the basic flow process of how this thing works. The steps you go through, right? The actions undertaken. Okay, now this sort of diagram is the sort of thing we might map out just to understand how our system works. So if Josh wanted to meet with Hassan, for example, a diagram like this would probably give Hassan, some understanding. A diagram for someone like Hassan, someone who's not a computer scientist, they can read diagrams like this and understand them quite well. In fact, in the health sciences, they create logic models that involve these sort of flows and branch points. They'll create those sort of things quite readily. So it's very understandable, very useful elsewhere in the development process. But my point today is that this is really useful for testing, for thinking about systematic testing. Because again, how could you claim without blushing that you've tested your system seriously unless you've gone through every transition here, right? Or at least that you've gone to every point here. If you've never tested the system could confiscate the card, how can you claim to have tested this? You haven't really tested it's working properly. Test that pieces of it are working properly, but not the system as a whole. Similarly, if you haven't verified that if your account is exceeded, it just rejects it and ejects your card. It doesn't actually debit the account. because you're overdrawn. If you haven't tested that, how could you be said to have tested this? So turns out the diagrams like this provide a really useful way of thinking through testing and systematically reasoning about what do we need to test. Here's another example. What does this diagram represent? Anyone? Well, it's a ticketing procedure. This may be tickets to a hockey game. It may be tickets to for travel, which is, I think, where it was originally indicated. So here, you may make a reservation, but you haven't paid yet. So it's kind of reserved the tickets for you, but you have to pay within a certain period of time. You pay it, and it can print a ticket. And which is later used, or maybe someone will want to return that ticket, will want to seek a refund. And if you were creating a ticketing app, I was once approached about years back about being a lead developer for, maybe the lead developer for Ticketmaster. And, here a diagram like this would make a lot of sense, thinking through what we need to do to sort of systematically test the system as far as is it working or not. And, basic face plausibility, we got to have tested it, to see if we can cancel it, for example, case where it's used and cancel where we made the reservation we didn't pay. But to test it more thoroughly, we really should be testing this case where we cancel a paid ticket before it's printed, or where it's ticketed and then we try to cancel it. So this is what's called transition coverage, not just state coverage, not where we've just gotten to this point, but where we actually cancel it. Okay. This is another flow diagram. This is actually for showing a repair situation. Okay. So where we're debugging a process involving repairing. These could be repairing computers, for example. Could be repairing iPads or what have you. So, you have various people in different states, in various situations, and depending if they're in the U.S. or European Union, you may offer pickup. Otherwise, you have to, you may have to send it to a maintenance station, etc. And we could do this sort of reasoning at the statement level, in fact, this sort of coverage. So we want to systematically cover certain structures at this level. So here, instead of dealing with broad states or actions, like here, we're dealing with actual individual statements. So we want to be able to at least say we've reached all of these statements. And the coverage tools that you use, things like Cobertura, they'll do this sort of testing. They'll make sure, what fraction of the statements have you actually gotten to. But as we'll see, that's not the be-all and end-all, because sometimes statements is weaker. Statement coverage is weaker than testing, for example, transitions. So the basic idea in this sort of coverage, folks, reasoning things through. I used to give several lectures on this topic. We just do not have time. The basic idea, though, for which I will hold you responsible, is we first identify the set of things we need to cover. I'm trying to make this kind of generic because there's a lot of types of coverage. So maybe we want to cover the states. We want to cover, that we reach each of these points, each of these basic blocks, using compiler terminology, which are sort of contiguous lines of code. There's no branches in them. If you start at the top of this one, you'll get to the bottom for sure. Okay. So here we have an example of statements, and we might want statement coverage. So we identify in 0 and 1 and 2. These are the things we want to cover. Or, ladies and gentlemen, we might decide that we want to cover, instead, transitions. Transitions here would be shown with these arrows. So, we want to not just get to each of these points, we actually want to cover these transitions here. Okay? We want to come in on this one, cover each of those. So we could say we want to cover states, we want to cover transitions, and each regardless, we want to identify which things we want to cover. Does that make sense in that first stage? Identify the set of things to cover. If we were dealing with this situation, the states might be these. We want to get to our tests, we want to make sure they get to each of these states at least once. Could you imagine that? We want to have at least one test where we actually pay for it. We want to have at least one test where we have canceled it without paying. Does that make sense? Okay. Similarly with this, there might be at least one case where we've gotten a situation where it's confiscated the card, at least one case where it's ejected the card, at least one where we're asked to select the account number, at least one where it prints the receipt or whatever. Okay? Okay, so we identify the things we want to cover, and that sometimes means drawing those diagrams. Then we develop a set of abstract scenarios like paths that include all the things we want to cover. So if we want to cover states, here we're dealing with path coverage type of situation. So, okay, we might have a path that comes in N0, goes to N1, and goes to N2. That path will cover these states. Now, to be a valid path, it has to start at a reasonable place, like the beginning of a program, and go to the end, to some valid end. And here, going through these states would be a valid path. That covers the states, right? Right? This path here covers the state. Ladies and gentlemen, does that path cover the transitions? Remember, I said you could look at the same diagram on the left here, either from the perspective of the states, N0, N1, and N2, or the transitions, these things shown as arrows, x greater than or equal to y, x less than y, the predicates associated with them, for example. So, with that path from the top, going to N0, going to N1 and N2, would that path cover all transitions?
No.
Okay, good. So what transition would it not cover?
The top one to the bottom one
Straight. Straight down. It wouldn't cover the case where essentially this predicate is false. Yeah. It's only covering the case where it's actually true. If we're trying to cover transitions, it's a stronger condition. We're going to be needing not just one path, but two paths. One going like this, and then one coming straight down. And those paths would collectively cover all these transitions. Right? Does that make sense? Now, those paths might also, there might be repeats in the transitions covered between those paths. That's fine. That's fine. It's not a problem. Okay, so you test some things more than once. Okay. Might test it under different particular data values, for example, or whatever. And sure, okay, you're always going on a couple paths from the very top of the program or what have you. Yeah, that's no problem. The question is how many paths, we want to have paths that cover with confidence all these points. Similarly, folks, this one on the right, you could ask, well, okay, suppose I want to cover all states here. Give me a path that would cover all states on the right. Again, the legal path, we're assuming it has to start at the top. We won't confine ourselves to, or we won't complicate our lives by thinking about what's outside of this. Suppose it has to start at the top. Give me a path in terms of where it would travel that would cover all states.
0, 1, 2, 1, or 0, 1, 2, 1, 3.
Okay, yeah, 0, 0, 1, 2, 1, 3 will be an example path that would cover all three states, right? Suppose I wanted a path that covers all transitions. Would that cover all transitions as well? Yes, it would. In this case, it covers all transitions just fine. Now, could you give me another specific path that would cover all states?
No.
Sort of. It depends on the interpretation of my question. You could have a path that goes at 0 and 1 and 2 and 1 and 2 and 1 and 2 and 1 and 2 and 1 and then 3. And you could say, well, oh, come on, that's just, it includes the first path. And fair enough. And there's notions of that. Yes, it includes the first, but it is another particular path. So folks, again, first step, identify the things you want to cover. So identify what are the states, right? Or what are the transitions. Simple enough. And then identify one or more paths, a set of paths that cover those things. Okay. And those have to start from the top and go all the way through. Okay, great. In this case, this is the end one. That's the end one. That's what showed it in bold. Okay. And then, that's not all, though. And this is, you're going to be responsible for this. I mean, about a month from now, you're going to be hopefully telling me this back to me. You're going to develop a set of concrete test cases that cover these paths. So what's that about? Well, folks, I mean, we've just been talking about paths that cover them, and that's all great and good. But I want you to give me now particular concrete values for x and y. So variables x and y hold some particular value, after all. Give me values that will lead you to exercise the path. So let's take the one on the left here. And 0, so we want to cover, suppose, all states. Give me concrete values. What's the value of x and what value of y will lead you to do this path that we talked about that would cover all states, and 0 and 1 and 2. Give me values for x and y that will actually lead it to go that path.
The y is set to 0, so it's not going to.
Okay, but we're talking about value of x and y up here at the top.
Yeah.
What one is gonna? So what inputs? What starting values for x and y would you use to make it go this path of coming down at 0 and 1 and 2? Give me
1 and 0.
Okay, so x is 1 and y is 0?
Yeah. That would be a false state. And then the other one, the other way around would do 0 and 1.
Okay, so there we'd be covering all transitions between those two paths.
Yeah.
But just for states, all you need is
Oh, sorry, states. Sorry.
x equals 0, y equals 1, right?
I apologize.
Yeah. So, no, I love people speaking up. And you got my next question, which is how do you cover all transitions? So folks, when you're creating test cases, that's how you got to be thinking, right? You got to be thinking, okay, what test case am I going to run? What's the value of x and y? You're thinking very concrete terms there. And the point is how you arrive at systematic coverage by formulating test cases. So this, again, is the basic recipe. You identify the set of things you want to cover. Nodes. You identify paths. And again, it's not just at this level. It could be at this level. You want to get to all the screens in your application. You want to get to all the web pages on your web app. At least once, right? How are you going to stand before me next Tuesday? Say, we tested our app. And I'm going to say, well, just clicked on it based on, the deliverable you hand in next week. Maybe I click on it, or I click through, I go to this certain screen, and it just dies. You say, well, we didn't test that screen. We didn't test that screen. We never got there. Oh, come on. You didn't test your app then, right? Same thing with a web page. I mean, so often, whether it's a web page at a high level, this sort of thing, you want to identify what you want to cover. You want to find the paths from start to finish that would go through that, and then find a particular case. So set up a card so that, for example, it's not recognized. You stick in your card for your driver's license, and it ejects it, right? Okay, we've tested that. Okay, now this other one, we'll get it to test in this other way. And you can then systematically test these things. So here, in this final thing, you're developing test cases, specific test cases, particular values for the input. So make it do your bidding. Make it go the ways you want for these, for example, these paths. Okay, so here's some code. This code, I think, goes from CGI encoding, so the sort of encoding that would be used for a URL, for example, in a web page, and it turns it into an actual path to look up on a web server. So we could map out this algorithm, which is in C and involves while loops and else ifs, we can map it out in this sort of way. These are our basic blocks. So if you reach, this point in G, you reach that first statement, it's going to be executing all through the next three, right? It's going to be going one after the other, and then it's going to branch, depending on whether it's false or true. So we've just rewritten this application, or just written this out to put it in this nice form. So suppose I said to you, okay, great. I want you to cover all nodes here. I want you to cover all states. All these basic ones, okay? Well, we have them nicely labeled here, up through M, A through M. It's a good start. So we've identified the things we want to cover. Now, we need to identify paths that will go through this code that will cover these things. Give me one path through the code, for example, that would cover some of those states. Give me a path through the code that would cover some of those states. Again, it needs to start at the beginning and go to the end. The end would be a return, for example. Okay. So, anyone? What's one path through the code?
A, B, C, D, F, L.
Okay, A, B, C, D, F, L. Okay.
And then B.
And then B.
And then C.
And then C. And then
D, G, H.
D, G, H. Yeah.
L.
L.
And then E.
Okay.
And then C, D, G, I, L.
C, D, G, I, L. Okay.
And then B again.
Okay. B again.
And then
Wow, you're going at it. Yeah.
C, E, L.
Good. L.
And then B again.
And then B again.
And then M.
Okay, and then M. So you have hit all the states. Remind me your good name, young man.
Region.
Wedro. Yeah. I would remember it on good days and on those. So Weizhong once again has hit the jackpot. So here he gave a path which hits all states. Now we don't need necessarily one path which hits all states, but that's a great one. And he systematically thought it through. Now, young man or anyone else, we want to actually create a test case, an actual test case that will exercise that path. Maybe Wei Zhong, he gave a great path, but maybe we don't just want to do it with one path. We could have said, okay, we'll have one path that goes up to L and then comes back, and then we'll have a different path, from the start, which goes and hits E, for example, or what have you. You don't have to do it all at once, although that's great if you do. That's great. Sometimes doing it not all at once might mean you find different things in each of those. For example, the one you just did, suppose there were a bug, in G. You hit that early on, and that might have prevented you. Maybe it has a null pointer error there, right? And in that case, it might have prevented you from getting to the point where you tried E. And if you divide into separate test cases, separate paths, maybe that would, let you not be blocked by this when you get there, or wouldn't be so ready. You could have a test case, which a separate test case would do A, B, C, E, L, B, M, for example. But Wei Zhong gave a great path. Okay, so the question is now, with Wei Zhong's path, could we find a concrete test case that will actually do it? And to do this, you have to look at the code and say, okay, what condition would make it go from B to C? Well, we need E pointer to not point to something that's the null character. So we need to sort of have the first thing in this, whatever this thing is, and it's this thing in the encoded string. It can't be empty, so we need to go there. And then, so let's see, at C, to make it go, I think the first time through you went to D. So we need the first character to be plus. right? To make it go that way, make it go from B to C, we need the first character to be plus, right? And then I think you did G. So to go from D to G, we would need the, okay, sorry. This is to be not plus. I misread. This is false. So to be not plus. And then, okay, we want it to go from D to G. That character therefore has to be one of these, right? And a percent sign. Go to G. And then, after G, we wanted it to go, I think you did H the first time. And so here, the high digit, okay, we'd have to figure out, okay, from the hex value here, we would need it, I think -1 encodes something that's not a hex value. So we would need something that's a legitimate hex value, and then it adds it up. So it's a legitimate set of hex values, like A, B, or something like that, or D9. And then it computes the hex value. So the point is, we're trying to come up with very concrete strings. Do you understand that? And this would be an example of a set of test case strings. So these test cases are concrete sets of strings, each of them, like T0. This gives a set of strings that will exercise this routine completely in the sense of test coverage for these states. So it'll be guaranteed to hit all of these states. So the first one in T0, any of these will do, I believe. Yes, any of them will do. The last one is like Wei-Zhong's in the sense that it tests all the states together. You could come up with this complicated string as a URL, and it would test all the states. Or you could test one with an empty string, one with the word test, one with the test plus case, percent sign, one adequacy, and here's another one like Wei-Zhong's. It tests all of them together. Here's another one, and just these will exercise all the states. So here we're going to particular test cases that will be guaranteed to hit all these states. Are people understand that? Okay, so ladies and gentlemen, and time is, it's the tyranny of the clock. What a torture. Man, I was gonna, just beautiful. The thing of beauty. But this is the thing, folks. I want to pose to you. I want to pose to you as a challenge. I want to pose to you as a riddle. I want to pose to you as a call to action. Can you, for your systems, give me at least a state diagram with transitions? Maybe these are pages on your web app. Maybe these are states. These are screens within your app. And you go from one screen to the other by enter medication information or by press the side effect button or whatever. And you show me these things. And then can you go from that to create test cases that will systematically explore these things such that you hit each of these, at least there's some test case that hits at least each one of these things. Can you show me that you have in fact hit all of these statements? And even better, could you show me that you've taken all transitions here, that you've tested the analogy of all cases where the card is not lost or the card is lost or the card is expired? If you could do this, I'd be really impressed. And if you can't at least test, you've gotten to at least some test case has confirmed that each of these places work, even if it's only manually. I'm going to say, have you really tested your app? Have you really tested your app if you've never even tested the case where the user's not allowed to log in? They've entered a wrong password, or they've entered a wrong login piece of information. I'm going to say, are you really confident that you've tested this? So you should be able to show me your test cases. We cover these states at least. Ideally, you could say, we cover those transitions. Each of those transitions, each case where a button is pushed or a link is pressed, you've tested each one of those in some test case. Manual, maybe. I'm not going to be really picky. Automated, great, even better. But if you could show me that you've tested each of those hits, that you've systematically explored this, you come up with some case that gets it to go the appropriate way, I will be a happy camper. Okay? So I want you to think about that. That's my challenge to you for the weekend. That's my challenge for Tuesday. And of course, I'd be delighted to discuss details of this if you wanted help. Past teams have done this. They've done a fine job. And I would hope for your testing that you can aspire to similar levels of robustness. Because, ladies and gentlemen, if you don't explore it, how do you know that I won't? If you don't get to each state, how do you know that I won't? If you don't have an explored a transition, how do you know that I won't? And discover a bug. So for your sakes, insulate you from the disappointment of the professor and test at least each state, and even better, test at least each transition. Because Dylan and I will pound your code. Pound at it. And we'll see if we can flight the black eagle hole. I'm going to have a hard time growing the goatee in the next week. Okay, so that's all for today. Thank you.